He's a quantum applications researcher for IBM Quantum in New York, Yorktown Heights, New York. He has done his PhD from the University of Chicago, and he has joined IBM in 2019. And he has since worked on developing quantum algorithms for NISQ devices. Today we will learn from him about Qiskit Pulse. I myself am very excited for this tutorial. And without further delay, let's hand it over to Nathan. We should start now, please.
Great, thank you. So here, let me go ahead and share my screen with you all. Put this into presentation mode. Hopefully you all can see the presentation and see the proper view.
Yes.
Hear me and everything? Great, fantastic. Thank you very much for that introduction. I'm excited to be here today and talk about Qiskit Pulse. I just want to say at the start, I sort of always say this whenever I give a talk, please interrupt me. I much prefer it when there's a lot of conversations and a lot of questions. I think that I enjoy that a lot more personally, and I believe it leads to an opportunity for you all to get so much more from the presentation itself. So as was said, today I'm going to be talking about Qiskit Pulse. I know that you had a bit of a conversation on sort of IBM hardware or superconducting hardware from Zlatko and Thomas yesterday, I believe. So I'm going to be doing sort of a quick recap of some of that content. There may be some overlap, there may be some slightly different things and some different perspectives, but I'm going to start off here in the sense that it helps sort of set up the conversation about Pulse and how the sort of control of the hardware underneath is important when thinking about how those quantum circuits actually operate. Once I sort of give a quick overview of the hardware and how some of the details of the hardware works, I'm going to jump into talking about calibrating single and 2 qubit gates. I'm not going to give a full extension on all the different calibrations, though if you interrupt me and ask me questions, I'll definitely elaborate wherever is appropriate. And then also I'm going to be talking about, say, how you get, you have an X gate when you operate a quantum circuit. How is it that you actually get that X gate? As well as, say, you have these C naughts. So a C naught is a nice little circuit abstraction, but generally when you're thinking about the actual underlying control of your hardware, it comes in different flavors, and you actually have to sort of do a little bit of work to get a C naught from whatever native interaction you have. So in the context of IBM hardware, the C naught is built out of a cross-resonance gate. So I'll give a bit of a discussion as to how one actually builds that. And then at this very end, I'll be talking about this idea of circuit transpilation. So this is the process where you take some idealized quantum circuit and you map it to a hardware. In this, I'm really going to be focusing how a gate-based perspective, so looking at the circuits abstraction versus a pulse-based perspective, can lead to different perspectives and views on how one can do these transpilations efficiently. And this is sort of an important thing when you're actually thinking about getting the most from real quantum hardware. If there's time, so I will come back. I'm hoping to sort of do a live demo from one of our Qiskit textbooks and show you some of the inner workings of how Pulse sort of operates. Then I'm going to have some Q&A. If there's time, then what I plan to do is sort of come back to the presentation here and talk about this idea of continuous gate sets. So this is some recent work that I was able to participate in with a few others at IBM. But basically, it looks at how you can take this cross-resonance interaction and scale it in a careful fashion in order to have a more efficient implementation of your quantum circuit. And this gets to this idea of sort of transpilation as well and optimization of your circuits. So with that said, let's go ahead and jump in and talk about circuit QED and really the hardware that IBM operates. So when thinking about circuit QED, there's going to be two important elements. And the first we'll start off with is the sort of superconducting simple harmonic oscillator right here. So this is something that has a capacitor and an inductor. And when you look at the Hamiltonian, it's sort of described by this, where you have charge on your capacitor here with the C, and then some flux going through your inductor with its inductance. When you look at how this can be physically realized, it comes in a few different flavors. One of those is sort of what's shown here, where you have some coplanar piece of metal that has gaps on either end. These gaps end up sort of being equivalent to some sort of end capacitors. Then what this ends up being is some inductive transmission line where there's capacitance to ground. And now the boundary conditions of this, as well as sort of the material properties and the length of this device, will ultimately sort of dictate the frequency of your oscillation. And it, in a circuit diagram looks or can be equivalently seen as something like this. So now simple harmonic oscillator, if you've ever taken a physics class, you know that this is sort of a physicist's favorite toy model. So you start off with this when you say take Newtonian mechanics. When you take this simple harmonic oscillator and quantize it, and so look at it from sort of a quantum perspective, what you end up finding is that your energy levels are sort of spaced out evenly by h bar omega. So though this is a very enticing device to use, and you may want to try and make this your sort of qubit straight away, you run into this issue that as you begin to drive your first energy transition, the 0-1, the thing that you want to get coherent control over, you're similarly going to drive your 1-2 energy transition, your 2-3, and your 3-4, just because they're all evenly spaced. So this ends up leading to what's sort of called a Fox state, in which you can't really get the coherent control of two energy levels that you would ideally have in order to actually sort of make a qubit where you can have a superposition of different quantum states between those two and what have you. Now, this element will be important regardless, and we'll get into why. But now the way that you can actually get use of the lower energy levels is through taking this linear inductance and adding a nonlinear inductance in place of it. So namely, that's where this idea of a Josephson junction comes into place. So now instead, if we take this capacitor and linear inductor and replace it with a capacitor and this nonlinear inductor realized through a Josephson junction, then you're going to get what's sort of referred to as an anharmonic oscillator. Now, the Josephson junction can be realized in a lot of different ways. It is the only known lossless nonlinear inductive element. Most commonly in the context of superconducting qubits, the way that this inductor is realized is through a superconductor insulator superconductor barrier, where the superconductor is aluminum and the insulator is aluminum oxide. This happens to just be something that gives sort of the best quality of junction. This is one area of research in which people try to engineer different sorts of Josephson junctions that have different properties, and it can end up being a very exciting field in its own right. When you do this and you replace this linear inductor with this Josephson inductor and shunt it with a capacitor, then you are realizing sort of a charge-based qubit, a charge-based superconducting qubit. There are a few different versions of a charge-based superconducting qubit, the most recent of which and the most advanced is known as the transmon qubit. So the transmon is where you're going to take a relatively large capacitance and shunt it by the inductance. To give you a sense as to what relatively large here means, basically what you do is you take the charging energy from your capacitor and the ratio of that to your Josephson energy, the EJ here, which comes from some inductive energy inside the Josephson junction, and that ratio should be, say, 30 or higher. So the EJ to EC ratio should be relatively large, and then that ends up putting you in this sort of transmon limit of charge-based qubits. Now, when you add in this nonlinear element, what you end up doing is now the energy spacings of higher energy levels begin to become more closely spaced together. So what this then allows is that now you can coherently drive on your 0-1 transition separately from your 1-2 and your 2-3. And then now all of a sudden you're able to get the coherent control between your 0 and your 1 state and actually start to operate this device as a qubit. Now, one thing I just want to say that's a thing of interest is the frequencies here of these devices tend to be around, say, 5 gigahertz. This 5 gigahertz, when you look at sort of an equivalent temperature of 5 gigahertz, it ends up being around, say, 250 millikelvin. So this is important because what this states is that you actually have to cool these devices down in order to ensure that they don't get sort of thermally excited by the environment. So a lot of the time I'll get a question about, oh, high temperature superconductors, and if you can make Josephson junctions with those. That is one potential way in which you can make a new sort of superconducting qubit. However, if the frequency of those devices are the same, you still end up having to cool the devices down to ensure that the environment doesn't actually heat it up. I did say earlier that so this qubit, or this Josephson junction with the transmon, this transmon, so Josephson junction with capacitor, is going to be the thing that operates is our qubit. But this linear resonator is still going to be quite important. Specifically, it's going to serve a few different functions. So one, it is going to be the thing that we use to read out the state of our qubits. And how that happens really gets into this idea of circuit QED, and I'll be explaining that in a second. You can actually use it as well to couple different qubits together. So when you see some chip photos of sort of IBM quantum hardware chips, you'll see that they're coupled together actually by these sort of coplanar waveguides like this here. And importantly, it's going to act as a noise filter. So the way in which it acts as a noise filter is, in a moment, I'll show you that you sort of couple it to your transmon qubit here. When you couple it, you're going to sort of couple it. Typically, you'll do it in a capacitive sense, but you can also do it in an inductive sense, actually. But when you do so, it ends up acting as a resonant filter from the rest of the microwave environment and helps sort of isolate your qubit, which allows it to get better T1s and T2s. And this may have been part of the discussion that you had when talking with Slatko and Thomas yesterday. So now, to give a sense of how the readout in this device works, I just want to take a moment and rewrite these Hamiltonians. So if you've taken a quantum class, you'll be familiar with these A daggers and A's. These are sort of known as ladder operators. So you can just view them as excitations or climbing up a ladder for the A dagger or climbing down the ladder for the A. And then for the transmon qubit, just for the time being, we're going to sort of approximate this as, say, being a two-level system where you have your sigma Z operator, which is telling you that your qubit's pointing either down or pointing up. Depending on the sign of this. And this omega Q is the frequency of your qubit, and the omega R is the frequency of your readout resonator. So now, when you couple these two things together, so here in this case, we're putting a capacitive coupling. This now is sort of what is known as circuit QED. So circuit QED is the circuit equivalent of cavity QED. So cavity QED is the thing that won the Nobel Prize by Dave Wineland and Serge Haroche a few years back at this point now. But this is the circuit equivalent. So you can really view this as sort of being so cavity QED, you have a physical cavity with some atom inside. Circuit QED, you have a cavity, which is this simple harmonic oscillator. And it is sort of the atom that is inside this cavity is the artificial atom, the transmon here. Now, the cavity of this is actually set by sort of capacitance plates that allow the light to sort of bounce back and forth inside this simple harmonic oscillator. Most of the time when operating for IBM hardware, we're sort of in a dispersive limit where you won't actually have a coherent exchange between these two systems. And when you are in this limit, you can describe your system roughly by this sort of dispersive Jaynes-Cummings Hamiltonian, which is written here. So you'll see that there's sort of this omega R with the A dagger A coming from that simple harmonic oscillator. You have your omega Q with the sigma Z for your qubit. But then now you have this extra term with a chi. So now this chi here, what this actually ends up being is it's going to be proportional to the amount of capacitance, say if you're doing a capacitance here, between your readout resonator and your qubit. And in some sense, this is dictating how strongly they're coupled. And there's a few different things that influence it. But so this here is showing the physical realization of such a system, say, in which you see that linear transmission line here. So this element here is going to be your simple harmonic oscillator. So this part right here is this. Then your transmon ends up being something that's sitting right here. In this case, you have some control line that allows you to tune this transmon in this particular case. And then it is now capacitively coupled to this through just sort of some coplanar capacitance between the center line and the transmon that you're interested in. What you'll sort of notice is that here this transmon in this diagram has two Josephson junctions. This gets into some details about how you can engineer transmon qubits themselves. And I'll also just quickly state that you can engineer a wide variety of different superconducting qubits. I'm just focusing on these fixed frequency transmon qubits that have a single Josephson junction. This is the one that we use at IBM. When you begin to change what sort of qubit you have, you'll end up changing the way in which you might decide to control the device as well. But in any case, staying focused on this sigma z, or sorry, on this chi with the sigma z, what you can note is that the effective frequency of your readout resonator, so this omega r plus chi sigma z, is all of a sudden now dependent on the state of your qubit. So if you're sort of thinking about this in an experimental sense, this says if I take some tone, some microwave tone, and I drive it and sort of drive it in one side and watch what comes out the other side. Well, if I change the state of my device, so the black, say, indicated the qubit being in the 0, and the red now indicates the qubit being in the 1, you'll notice that there's a difference in sort of how much will be transmitted through. And then from this, now all of a sudden, you can determine the state of your qubit, this sigma z. Putting in a slightly different perspective, say, if you sort of sweep what frequency you're driving at and watch how much is sort of going outside the cavity here, you'll find that you have a peak that is dependent on the state of your qubit. And it is this way that you can actually begin to do qubit readout of your device. So namely, let's say I go and drive this readout resonator at this frequency right here. If the qubit's in the ground state, I'll see a lot of transmission. And if the qubit's in the excited state, then I end up seeing a lot less transmission. And so that, say, is one way in which the amount of transmission going through can help you determine what state your qubit is actually in. So now now I want to just put this essence of measuring the qubit and how the physical things that I was just describing connect to what you see when you operate on IBM quantum devices. To give you a sense, what you generally do is you're going to first do some operations on your qubit. This is part of what we'll be talking about in the next sections of this talk. And then you end up doing, as I just said, probing the readout resonator and seeing how much transmission you have. When you operate sort of at the quantum circuit level, or what we sort of often refer to as measurement level 2, this ends up giving you back a 0 or a 1. But there's a question now of how is it that you actually get the 0 state and the 1 state based on this? So I sort of described it can be based on the transmission. More specifically, what this ends up looking like is what you see in measurement level 1 here, where you're going to send in a microwave tone. That microwave tone is going to have some real and imaginary components to it. So this here is now plotting the real and imaginary components of that microwave tone. And then based on the state of the qubit, you see sort of these different scatter plots. Where if your qubit's in the 0 state, you end up being, say, on this section over here. And if your qubit's in the 1 state, you end up being on this section over here. And it's in this way now that you can sort of construct some method to determine whether your qubit's in the 0 state or in the 1 state. This, I think, is an area where people do a lot of research. You can do a very simple... Sorry, is that a question? Okay. So what was I saying? So you can do this in a very straightforward way where you say sort of take some decision boundaries that say it's somewhere in between the two and just say if it's on one side of that boundary, it's going to be a 0. And if it's on the other, it's going to be a 1. But this here is just one way where you can actually construct a discriminator, say, between your 0 state and your 1 state. And now there's something that goes one level below this. So this would sort of be what we're calling measurement level 0. This presently isn't available in Qiskit just because there is a supreme amount of data that has to be sort of dealt with when doing this. But these microwave tones have some characteristic duration and a time signal throughout that duration. Measurement level 1 sort of averages up that time duration and then gives you 1 point here. So one of these dots ends up being the sort of timed average result of some given measurement. But in principle, you could have this measurement level 0 where you could watch the time dynamics throughout your measurement. And that itself ends up sort of giving you more ability to understand exactly how the readout of your device is working. And then you can start to do more sophisticated readout schemes when having that ability. So this measurement level 0 is something that will eventually become available through Qiskit in the not too distant future. Let me go ahead and stop here and just see, are there any questions that I can answer or?
No questions so far. I don't see any questions.
Great. So now I'll just quickly give this essence of how the tune-up of your qubit can work. So here is some measurement pulse. It's going to have a characteristic amplitude dictated by the height in this box here, as well as some characteristic duration, say. And then now here you can see this sort of control pulse for the qubit on D0. So D is sort of driving the qubit and M is measuring that same qubit, M0. And so I will do 2 experiments that sort of lead to this plot that you see at the top. Namely, I'll do one where I have a pulse here and then I do a measure that leads to these red dots. And then I have another experiment in which I don't have the pulse and I just do the measure, and that would be these blue dots here. How you actually get this pulse is what we're going to talk about in the next section, and this gets into the essence of how you calibrate your single qubit gates. But for our readout pulse, if we take this amplitude and instead reduce the duration of it, what you'll end up finding is that if you reduce the duration too much, these 2 centroids begin to sort of come together. And now you can sort of imagine that discriminating whether you're in the 0 state or the 1 state, if your measurement pulse is too short, becomes much harder simply because these things are not well resolved. Now, this might give you the sense that you want to go in the opposite direction then. I want to take my measurement pulse and I want to make it as long as I possibly can. This actually isn't necessarily a good thing in the sense that if you begin to make that measurement pulse too long, what you can actually end up having are sort of an increase in readout errors. So namely, let's say you measure your qubit and at the start of your measurement, it's in the 1 state. Well, these qubits are very sensitive and don't retain their information forever. So if your measurement pulse is too long, you actually end up decaying throughout your measurement pulse. And if you sort of squint here, you might be able to convince yourself that in this case, there's some where there are more red dots where the blue dots are centered. And this is sort of showing that you've decayed throughout your measurement pulse. So now this is something that actually leads to readout errors. And this is one area in which you can actually begin to improve the results from your underlying hardware is when you sort of do readout error mitigation. And there are some different techniques. Some of them say can be based on the control of your device and sort of making use of, say, higher energy states. I will get to that if it seems to be of interest. But for the time being, I would like to move on and actually start talking about the calibration of single and 2 qubit gates. So here, this is where I'm going to get from this essence of the X gate that you see in your circuit and how you actually achieve that X gate. It's through this idea of a Rabi oscillation, which I'll explain. And then also, as I said earlier, how do you actually get that C0 based from the cross-resonance interaction? So same thing as before. We're going to do some experiments in which we drive our qubit. Here I'm skipping one step in that you actually need to find the frequency of what your qubit is. So the example notebook that I have spun up will be something where we can actually take a look at this and see how it's done. But then, so the typical way these experiments work, they're 2-tone experiments. You drive your qubit and then you measure the state after driving. So this qubit this qubit drive and measurement tone are going to have, say, some characteristic duration and amplitude. And what I would like to do for the sake of my explanation here is let's keep the duration of these things fixed. And then we're not going to adjust the measurement tone. We're going to keep it in sort of some optimal thing based on the previous slides. But now I want to start looking into how do I drive this qubit and how do I adjust, say, the amplitude here. So if my qubit starts off in the ground state, this is something that has variety of ways in which you can do this. Generally say, let's just use the nice property of physics that everything likes to cool down to the ground state eventually. So we'll leave our qubit, let it sit there for a bit. Eventually it'll cool down to the ground state. This isn't necessarily the most optimal way to ensure your qubit's in the ground state or the most efficient, but it is a very reliable one. So we'll let this cool. And then now we're going to go ahead and do this experiment where we keep our duration fixed, but increase our amplitude. And as we start to increase the amplitude, what we'll find is that the qubit is starting off in the ground state, but begins to precess about the Bloch sphere until it gets into the excited state. Now, if you were to continue increasing the amplitude, what you actually end up finding is that it will oscillate back and forth. So start off in the ground state, go to the excited state, and then back down to the ground, and then back down to the excited. And these oscillations here are sort of known as Rabi oscillations. Now, it's these Rabi oscillations that allow you to get that X gate. So in principle, a rough calibration of your X gate would come from doing what is known as a pi pulse measured from the Rabi oscillation. So namely, the pi pulse or the pi aspect of this just refers to the angle of rotation on your Bloch sphere. And then you can see here, this ends up being the thing that allows you to say, aha, we're in the excited state when we've reached this point right here. Now, this is a rough calibration, and I'll actually get into some details as to how you can get, say, a finer calibration on this. One thing I sort of want to say is that I talked about the pulses, say, having a characteristic amplitude and duration, but they also have some interesting shapes associated with them. So right here, say, is some sort of Gaussian type pulse. And then actually we use this idea of, say, a drag pulse. So drag pulse stands for derivative removal by adiabatic gate. That's the drag element. What this drag pulse does is it's a Gaussian pulse that on top of this Gaussian, you are adding sort of a pulse that, or an amplitude that's sort of equivalent to the derivative of that Gaussian. The reason that you do this is that it helps suppress leakage errors. So what are leakage errors? Well, I want to take my qubit, and when I'm operating my qubit, because it has some finite lifetime, I want to make my operations as fast as possible. However, I start to run into an issue that if I take my Gaussian pulse and make it very short, too short, I can start to have issues in which I leak outside of that 0-1 space. So the other frequencies, though they are now not equivalent so that I actually can get coherent control, they're not necessarily infinitely far away. And so now as you begin to reduce the duration of your pulse, you start to incur sort of other frequency components, and you can get excitations into higher energy states. This drag pulse here helps reduce how much you sort of have those leakage issues. This is one way in which you can reduce the duration of your single qubit pulses. So doing this, most IBM backends, say right now, have this tuned up to be about 36 nanoseconds. Some of our recent updates for quantum volume 64 that we had done quite some time ago will allow these single qubit gate durations to be even shorter, say around the order of, I think, 25 or 20 nanoseconds. The absolute fastest single qubit gate that I've seen was from some colleagues out at Zurich, where they did a 5 nanosecond qubit gate with no evidence of leakage outside. When they did that, they had to do very sophisticated readout schemes and resetting the qubit in careful ways. And they took basically a 24-hour period of sort of using machine learning to actually learn how to do this gate effectively. So it's a non-trivial thing to get such fast gates, but it is an active area of research. Now, to talk about how, earlier I mentioned this idea of doing rough Rabi oscillations and how that gives you a rough calibration for this X gate. To actually get fine calibrations, I just want to give you a little bit of a sense what you do here. To that end, I'm going to, instead of being at this pi pulse, I'm going to move away from the pi pulse and move to sort of this pi over 2 pulse. To first order to do this, I'm just going to assume there's some sense of linearity here in the sense that the amplitude that gave me a pi pulse, half that amplitude will give me a pi over 2 pulse. This assumption of linearity does become important in different contexts, and I can elaborate on that. But if you are doing this pi over 2 pulse, So now we have some pi/2 pulse here. And let's say that I actually do this in it. So if it was perfect, I would do this pi/2 pulse and it would put me right on the equator of my Bloch sphere. However, what I end up finding is that, I can model, is that it's actually going to be off by some amount epsilon. So this is some slight sort of coherent error that I want to try and reduce.
is increased by 0.1 mole per liter. ID कितना हो गया 9. ID हो गया है 900.
Sorry, Disney, is that a question?
I don't think so. Please, everybody unmute.
Okay.
Mute yourself.
Okay, so now we're off by some amount epsilon, but this amount epsilon is going to be so small that I can't actually resolve it just from these Rabi oscillations. So what I will do is this idea of error amplification. So error amplification is quite common whenever doing sort of pulse calibrations and trying to tune your gate up. What that in essence does is take your gate and repeat it some number of times. So it's off by some amount epsilon. If I repeat it 3 times, it's going to be off by an amount 3 epsilon, 5 times 5 epsilon. And then if you do this, what you end up sort of seeing is that you get what we sort of refer to as these ping pong type things, where you sort of start off, say, being around the equator, but not quite. But then dependent on how many times you repeat that gate, you sort of amplify yourself further and further away in this ping pong type fashion where you're bouncing back and forth. And it is through this sort of error amplification protocol that you can now finally adjust what that amplitude is and reduce how much coherent errors you have. So then by doing this, now you sort of finally calibrated your Rabi oscillation or your Rabi amplitude or your pi/2 pulse amplitude. And then now you can begin to do a variety of different sorts of fine calibrations as well. One that I'll slightly touch on is this idea of doing fine frequency calibrations. To get into this idea of fine frequency calibrations, I want to first talk about the virtual Z gate. So here is how I've talked about how we rotate about, say, the x-axis or y-axis. But then there's a question as to how do you rotate about the z-axis? So this is done through the virtual Z gate. I very much so like my colleague Nick Braun's phrase here, the only perfect gate that you have is the one that you don't do. So the virtual Z gate is a gate that you actually achieve by adjusting the phase of your classical control electronics. By doing so, you end up sort of determining whether some pulse is rotating about the sigma x-axis or about the y-axis. And so it's in this way, through adjusting the phase of your classical control electronics, that you can adjust which axis you actually end up rotating on. So this Z gate comes through just adjusting the classical electronics phase. Now, through the combination, say, of that pi/2 pulse with the virtual Z gate, we are now in a place where we can do arbitrary single qubit state preparation. So now I can take my qubit, my single qubit, and I can place it anywhere I want on the Bloch sphere. Now, what this also allows you to do is this essence of Ramsey oscillations. So Ramsey oscillations says you take this pi/2 pulse, you wait some period of time, and then you do another pi/2 pulse. And then when you do this, you end up getting these oscillations that are sort of seem somewhat similar to the Rabi oscillations in some sense, but are known as Ramsey oscillations. These Ramsey oscillations then actually are how you can begin to do fine frequency calibration and sort of get the frequency of your qubit to a very high level of precision. What this also allows you to do is, say, measure the T2 of your device. So through these Ramsey oscillations, you can measure the T2 to give you an essence of what the T2 is. So this is sort of the thing where you put your qubit in a superposition state. How long can you actually read out that superposition state? So that's your sort of what's known as your T2 star if you just do that Ramsey oscillation with no pulse in the middle. You can also sort of add these pulses in the center where you say do an echo, and these are a way in which you can help improve the coherence of your qubit. So this is the most basic version of dynamical decoupling. And this is something, say, that you can try and do. It's a place where people do study to see if you can use this dynamical decoupling to improve the quality of your results. And this is, say, one way in which you can begin to do research on our backends is through seeing how dynamical decoupling schemes can, say, help an algorithm or not. Those are the basics on how you calibrate single qubit gates. There's more details and a lot of interesting things that you can study even with these single qubit gates. Out of the interest of time, I just want to get into these 2 qubit gates instead. So up here, I've sort of shown, say, a prototypical thing one might want to do with a 2 qubit gate, namely prepare this Bell state, or more generally, say, a GHC state. So this is where I do some Hadamard gate, then I follow it with a controlled knot, and then this puts me into sort of this maximally entangled 0, 0 + 1, 1 state. So now, how you achieve this 2 qubit gate will depend on the hardware. For IBM hardware, we do this using what is known as a cross-resonance gate. To give you a sense, so here we have our 2 qubits. They're coupled together by that sort of transmission line that I was mentioning earlier. And the way that our cross-resonant gate works is we're going to take qubit 0, and we're going to drive qubit 0, but we're going to drive it at the frequency of qubit 1. When we do that, it leads to this sort of interaction, where the important thing in this interaction is this ZX term. This ZX term is actually the thing that will allow us, is the necessary primitive that we need in order to get a controlled knot. I'll walk through how exactly that works in just a second. But I also want to point out that the cross-resonance gate comes with other interaction terms as well. So in this case, we have an IX and a ZI, and there's other terms that actually sort of go beyond these 2 as well. These terms are not the ideal thing we necessarily want. So when we construct our C0 gate, we're going to have to come up with a way to remove these terms here. And I'll walk through how exactly it's done. But for the time being, let's go ahead and assume that we have only this ZX interaction. And how is it, once we've gotten rid of these other terms, that we can build a C0 from the ZX interaction? Well, if you take your Pali matrix, the Z Pali matrix and your X Pali matrix, and you do Z sort of direct product with X, and then you exponentiate that with some sort of arbitrary theta, this is the sort of matrix unitary that you end up evolving. Now, sort of suggestingly, I'm going to pick one value of, say, pi/4. This isn't going to quite be the C0, but what you'll end up realizing is that if you take pi/2 of the ZX interaction, and then also do these other rotations of ZI negative pi/2 and IX negative pi/2. So this ZX is our 2 qubit interaction, and this ZI and IX are both single qubit interactions, and they're sort of pre and post rotations that you do in order to get the clean C0. So if you sort of go from this situation in which you have a ZX of pi/2, look at this matrix, and then add in these 2 matrices right here, it'll sort of naturally fall out that you end up getting this C0 right here. And this is something that maybe I can show how some of this looks when we're operating with Qiskit, actually. So this is now how you end up taking that ZX interaction, and you get the sort of ideal C0 that you want. But as I mentioned earlier, there are these other undesired interaction terms that we want to remove. So to remove them, we need to do some extra work. So to that end, let me just go ahead and show you what's going on with our C0. So this right here is a calibrated C0 gate from our backend. The cross-resonant tone that I refer to is sort of this yellow component right here, or orange component right here, as well as this one. So this cross-resonant tone right here leads to these different interaction terms. So it gives you the ZX, which is the thing that you need in order to build the C0, as well as the ZI and the IX. But now you can see that our C0 has some other terms going on here. So how exactly is it that we or what exactly are these terms? So some of them are going to be the terms that I referred to here, the ZI and IX, and I'll point it out in a second. And then there's also some terms that we use to get rid of these undesired terms. So specifically, first, there's this idea of an echoed cross-resonance. So earlier I mentioned this idea of dynamical decoupling. Well, the echoed cross-resonance is in the same spirit of dynamical decoupling. Namely, you can insert these pi pulses, and what they do is they allow you to remove certain interaction terms. So in the context of our C naught, this echoed cross resonance helps, say, remove this Zi and this Ix interaction term. Now, there's some other things going on here. Namely, you might see that there are these rotary terms up here. So these are some extra terms that exist on our target qubit. We add them, and what this is actually removing is one of these interaction terms that I didn't originally show. So namely, it's this ZY interaction term. So by adding this rotary term here, this now ends up helping ensure that we sort of get the isolated ZX interaction that we ideally would like to have. So it's through all of these that we then get the CX interaction. And then now that ZI and IX rotations that I mentioned, so this little knob right here, this is the virtual Z gate of -pi/2. And then this pulse right here is that IX of -pi/2 pulse. So it is now through all of those different pulses that we've ultimately achieved getting the C naught gate that we want. Let me go ahead and pause. Are there any questions?
Not that I can see.
Okay,
there are no
great.
questions in chat box.
Great. So this is how you can build the C naught from a cross-resonant interaction. I'll say this is an area in which a lot of people do interesting research. So I'll just, at a high level, mention there's this idea, say, of a cross-resonance interaction where instead of just driving one of your qubits at the frequency of the other, you can drive both qubits at the frequency of the other. And this is sort of known as the cross-resonance gate. A recent publication from some colleagues out in Japan published on this. And what's nice about this cross-resonance gate is that it allows you to implement swap gates more efficiently. So I just bring this up to say that there's also actually this idea of a direct C naught that was a part of some of IBM's improvements in quantum volume. The direct C naught basically achieves this the removal of this CI and IX term without actually needing the echoed cross resonance. So you can sort of do it directly and you get rid of these two pulses here. So in that way, you can actually make your gate a bit shorter in duration. By making it shorter in duration, this ends up being a theme a lot of the time in improving the underlying quality of the gates, is reduce the duration while not getting any sort of undesired interaction terms. So with that said, I want to now move on to this idea of circuit transpilation. So this is now thinking about how we map some idealized quantum circuit onto the actual hardware, specifically highlighting how a gate-based perspective might give you different results than a pulse-based perspective. Just to give you a sense of what this problem actually looks like. So let's say this is the circuit I wish to evolve. So this is perhaps a circuit you'd be familiar with if you've looked at Bernstein-Vazirani algorithms at all. But in essence, this is, say, for most qubits applying a Hadamard, you have an X on the bottom. Then you're doing a C naught between Q0, Q4, Q1, Q4, Q2, Q4, and Q3, Q4. That's the ideal thing you want to do. But then now if you go and look at some real hardware that you have, so it'll change what the connectivity of your hardware is. But using one example, so here we have a 5-qubit device. So we can put all of these qubits on here. But what we can see is that Q0 does not talk directly with Q4, but you need a C naught to happen between Q0 and Q4. So this then says, okay, well, now I have to actually insert a swap gate so that I can actually get Q0 to talk to Q4 at some point. Long story short, you can do this transpilation process sort of intelligently and you can compile it well, or you can do it poorly and add in a lot of redundant, unnecessary C naughts and a lot of gates that you don't necessarily need to do. This becomes important because if you do it well, there's a good chance that the answer you're seeking will sort of stand above the noise. But if you do it poorly, then all of a sudden what you'll see is that the correct answer, the thing that you're actually trying to achieve and use this quantum computer to get, will be buried in the noise. And because these devices are very sensitive, you have to be rather intelligent in thinking about how to transpile this effectively. So now in the Qiskit perspective, the transpile function is a built-in thing. At the very basic level, so namely this idea of optimization level 0, what the transpile function will do is take into account what the connectivity of your device is and then do the minimal mapping that it can. However, there are these different levels of optimization, 0, 1, 2, and 3. And as you move higher up in these optimization levels, they will help from the gate-based perspective, make this circuit implementation more efficient. So for example, level 1, I believe, it will see that you have 2 C0s or two of the same gates right next to each other, and it will collapse those down when they say are equivalent to an identity and help reduce the fact that you don't need to do 2 C0s if they're right next to each other, at least in the sense of trying to get the least noisy circuit that you possibly can. But now these transpilation functions, most of the time, end up coming from this gate-based perspective. So this is where they take those idealized boxes of this X gate or this C0, and they don't pay attention to the fact that there's a lot of underlying pulses that are inside that C0, say. So an example of where this might arise is, say, the open C0. So in the case of the open C0, so this is where instead of, so the regular C0 takes my control and it will flip the target if the control is in the 1 state. The open C0 does the opposite. It will flip the control if the qubit's in the 0 state. From the gate-based perspective, the way that you can do this is you just add a gate, an X gate before and after your C0. And this ends up sort of from a circuit-based perspective being equivalent to an open control knot. When you look at the pulse perspective, you can end up seeing something like this, where here I've highlighted, so these 2 pulses at the beginning are this X gate. This pulse right here is a part of that C0 gate that allows you to actually get the C0. So this is the IX rotation that I had mentioned earlier. And then this pulse right here is this X gate. This right here actually ends up being more efficient to implement if instead of adding these X gates, you just flip that IX interaction. Instead of doing a negative pi over 2, you do a positive pi over 2. So that's sort of what's shown down here at the bottom. And now if you worked out the matrix unitary for this, what you'd end up finding is that you actually are, this here is equivalent to an open C0 as well, up to some global phase. And then you've now all of a sudden reduced how long this is going to take by 2 single qubit gates at the least. So this is, say, one way in which now, if you're carefully paying attention to the pulse level details, you can see that you have a more efficient implementation when you start to look at the underlying interaction terms themselves. Now, another thing I want to point out is the reversal of a gate. So at the circuit-based level, you have a C0. So say if you're controlled on the 1 and the target is 0, then what you do is you drive qubit 1, so through this U0 channel, and then at the frequency of qubit 0. So here you can see that qubit 1 is being driven in, with the cross-resonant tone on U1, and then you have all the various components that I talked about earlier. Now, if you wanted to reverse the direction, so I wanted qubit 0 instead to be my control qubit, and I wanted qubit 1 to be the target, then this, naively you'd say, okay, well, then I'm just going to take qubit 0 and drive it at the frequency of qubit 1, and then tune up my gate and do all the things there. However, there are 2 reasons I'll point out as to why this may not necessarily be good. One is that the cross-resonant interaction is somewhat asymmetric in the sense that one interaction direction will lead to a faster gate than the other interaction direction. And because of this, if you want sort of the fastest gate that you possibly can have, and this has to do with the relative frequency of the qubits, then you sort of want to tune your qubit gate up in the direction that is fastest. That's one reason. The other reason is calibration overhead. If I'm to tune up all these different gates and I have to tune them up somewhat regularly because systems drift and you want to make sure that you have the highest quality gate that you can, well, if I'm trying to tune up both directions of all my C0s, that's doubling the amount of calibrations that I have to do and reducing the sort of operational time for the device. So instead, what you can actually do is through you can reverse the direction of the C0 through sort of a Hadamard reversal, in which you apply Hadamards on all sides of your C0 gate. So you go both before and after on both the target and the control. And then by doing so, you now flip the direction of your C0. And so if you looked at, say, the instruction schedule map, you'll see that the CX for 0, 1 isn't driving qubit 0 with U0. So if you look at U0 here, there's no tone, there's no cross-resonant tone here. But instead what you've done is you've added some Hadamard gates after. You've also added it before. What you're just noticing here is that the Hadamard gates are sort of being enveloped inside the pulse here. So it's in this way that you can actually achieve the sort of reverse direction C0. Sometimes, depending on what you're trying to do with the hardware, being aware of the fact that the hardware, the reverse direction of your C0 is sort of done through this Hadamard reversal, this can impact different gate constructions if you start to try and do gate engineering on our devices. So then one thing I just want to get to before I start talking through a demo and take some Q&A, and this starts to get to this advanced idea, which I'll talk about more, is this idea of these controlled RZ gates. So this, say, is important when you're thinking about QAOA, so quantum approximate optimization algorithm. Or for this specific case, say the Pauli feature map for quantum machine learning type circuits. So this controlled RZ for, say, this angle of pi, when you use the basis gate sets of U1, U2, U3, these are sort of the universal single qubit gates, and C0s, then what you end up finding is that the transpile function will transpile it to something like this, where this is equivalent to 2 C0s with some U1 gates or some RZ rotations in between. Now, this is done sort of at an optimization level 0. So I'm not trying to do anything sort of efficient. But if I take this specific angle of pi, so this CRZ of pi, what I end up finding is that this is actually equivalent, say, to doing it with only 1 C0. So here, because of just the way that this unitary works, is that I can achieve that same CRZ of pi with only 1 C0, but then now some single qubits instead. So you can sort of see this come up at optimization level 3. But more generally, if I were to do this for, say, a different angle, so controlled RZ of, say, pi over 2, then whether you do optimization level equals 0 or optimization level equals 3, when thinking about the gate-based perspective, 2 C0s is the most efficient way in which you can actually achieve this transpilation. But this now is where we get into this idea of continuous gate sets. I'll come back to this. I first want to jump to a Jupyter notebook in which I do some sort of live examples of Rabi oscillations and qubit frequency detunings. If we have some time, though, I'll come back to this sort of continuous gate set. So I'll say thank you here. I'll pause for some questions. While pausing, I will also bring up my notebook. Give me one moment while I find it. Please feel free to speak up and ask questions.
I don't think there is any question in the chat box, but I have a question. So when you say cross resonance gate, does it mean like it's like a Toffoli gate, or is it something else?
So yeah, good question. The cross resonance gate is not a Toffoli gate. Actually, it's interesting you bring up the Toffoli gate in the sense that, so a Toffoli gate is not a native gate in superconducting qubits, at least not as it is right now. And you can compile this, when working with qubits, you can compile it to 8 C0s is the most efficient way to do it. But something that's interesting, and is a sort of personal research of mine, is you can use qubits. So the transmons do have higher energy levels that you can make use of. And those higher energy levels can allow you to implement a more efficient Toffoli gate with qubits. But so the cross resonance gate is not a Toffoli gate. it's slightly different. In fact, let me just go ahead and do this. I will bring up cross resonance gates. And in the chat, I've posted the archive paper. So this is the cross resonance gate. What the cross resonance gate does is that through what I was saying, instead of driving one qubit at the frequency of the other, you drive both qubits at the frequency of the other. And by doing so, you can take a swap gate, which usually requires 3 C naughts. So sort of C naught in one direction, flip it, and then C naught again. And those 3 C naughts have some error. This cross resonance gate was shown that it can reduce that error by 50%. So that's the cross resonance gate.
Okay, so is that gate is it a user level gate or it's just in the labs right now?
Fantastic question. So in principle, if you read that paper and you had pulse access, you could go and tune up the cross resonance gate yourself. It is not made available by default. So it's not something that's sort of provided through the instruction schedule map, which I'll sort of show in a second with the live demo that I'm about to do.
Okay, thank you.
Of course. Great. So it seems like there are not other questions. So I will share my notebook again. So here is a Jupyter notebook. Shreya, can you just confirm and make sure that you see this?
Yeah, we can see this.
Great. So this right here is actually, so it's from the Qiskit textbook, Calibrating Qubits Pulses. So this is chapter 6 in the Qiskit textbook, I believe, and this is sort of 6.1. So I'm here and I just want to show you some of the things in this, sort of do some live demos and show you what's going on. But you can go through this whole notebook yourself and carry out all of the experiments going on. Specifically, what I think is very cool is that this is made available on the device IBM Q harmonic. So this is a single qubit device, so you only have access to 1 qubit on this device. But what's nice is that it's in the open and we have pulse level access. So if you wanted, you can start to go and do these experiments yourself. And actually start doing Rabi oscillations and Ramsey oscillations and everything. I think this is this whole idea of pulse level access in my mind is very exciting, in the sense that the only reason I was ever able to do it myself is because I went and got a PhD and spent my time working in a lab building these things. Took many years and it was a lot of effort. Whereas now anyone can get on the cloud and do this themselves, which is really cool. So in here, I'm just going to set up harmonic as being my backend through loading my count and using the open provider and harmonic here. Now, one thing I mentioned earlier is this idea of the instruction schedule map. So if you take the backend, has some defaults, specifically it has this instruction schedule map in the defaults. So now if you look at this, this now is where you can start to look at things. So if I get my X gate, and I'm going to go ahead and draw this. Now here you can see that this is a gate that has some sort of pulse with a given duration and amplitude. Now I believe if we wanted to do something like this, so let's go ahead and say SX sketch equals and then X sketch here. And then now I hope test sketch equals schedule. And let's say test sketch plus equals schedule is not defined, so let me just do this from Qiskit import schedule. Okay, so I guess I will instead just stick to showing you the things that you can get from the back end. So what I was hoping to do is sort of show you how the amplitude of the SX is half that of the X, but just because we can't do that easily, here's your SX. Then now if instead I wanted to look at my CX gate, here now I'm gonna need 2 qubits. This is harmonic, so it doesn't have 2 qubit gates. Okay, so I'll come back and show you 2 qubit gate if I have access here. But ultimately, this instruction schedule map here is showing you that you have some pulse, it's on D0, the qubit 0, and there's various things to this. So now what we're actually going to do, so this is an X gate that's tuned up already from the back end, and it has some characteristic frequency, but now we actually want to go and tune this up ourselves. So let's begin to do that. So first, this is just sort of saying, hey, we're going to make sure that we actually have pulse level access. So something you'll notice, this x-axis right here is in units of dt. dt is just a convenient way of referring to the time resolution of our backend. So in the case of RMonk, in most of our backends, this resolution ends up being about 0.2 nanoseconds. So very fast. Which is a nice thing. So just some helper functions. So now the first thing that we're gonna wanna do is a frequency sweep. So this is the thing that I sort of skimmed over at the very start. To do this, what I'm going to do is I'm going to set up an experiment. So I'm just going to be driving qubit 0. I'm going to take the center frequency. So this is already calibrated. If this wasn't calibrated, you'd have to be able to get a sense as to what's going on or know what's going on beforehand. But right here, you can see that this right here for the qubit of interest is the frequency of the qubit. So we happen to already know what the frequency is, but regardless, we're going to do a sweep and sort of show you what would happen if this was something that you wanted to do yourself. So now we're going to go ahead and take that center frequency and we're going to do some span around it. So in this case, say we're going to do 20 megahertz on each side, so a sort of 40 megahertz span. And then we're going to take steps of 1 megahertz at a time. So we can go ahead and run this. So now we've set up the desired frequencies to run from 4.951 up to 4.991 gigahertz in steps of 1 megahertz. Now, this right here, so this get multiples of 16. This has to do with how the sort of arbitrary waveform generators actually work in the sense that they operate, so they have a time resolution of 0.2 nanoseconds, but they ideally are sort of specified in chunks of 16 dt. So this right here is just ensuring that whatever you provide to the backend comes in this multiple of 16 dt. So then now, to start, what we're going to do is we're just going to take some drive amplitude, and we're not going to worry about tuning it up very precisely. We're just going to keep it fixed, say, around 0.05, and then we're going to sort of set the durations of this pulse. So then now, what we're actually interested in doing is sweeping the frequency of the qubit. So to that end, this is where we're going to do this in the schedule LOs. So here, what we're doing, so pulse.build pulse, we're building for the backend, and then we're setting the duration of the drive pulse. This is where we're setting it to some multiple of 16 based on how long we wanted the pulses to be up here. Then you have sort of the rise and fall of these aspects, and then you specify what channel you want it to be on. So the channel corresponds to what qubit you're actually going to be driving. And then importantly, pulse.set frequency. So now this is where we're going to take the frequency and we're going to set it and sort of sweep this frequency right here. So now that we've done that, we do this pulse.play, where we then take that pulse with all the specified details that we had set here and do a Gaussian type pulse. So this is going to be the Gaussian. So if you wanted the next step, say, would be your drag pulse, where you then sort of calibrate that derivative component of this. And then in order to actually see what's going on, we have to measure our pulse. So we do this pulse.measure. And here we're just sort of extracting the measurement pulse from the backend. Okay, so now here we're going to go ahead and set the schedules. So this set frequency is going to then allow us to specify which frequency the qubit's being driven on. And then now let's go ahead and run this. And now we can go ahead and look. So here saying now is some pulse that has the characteristic duration that we've set, and then there's some frequency right here. So now what you'll see is I go through, so let's say I look at the 10th one, nothing's looking too different. We're adjusting the frequency of the qubit, and we're seeing some differences in what this does, say for this delta F, so the sort of virtual Z rotation that we're doing at the start. But ultimately, we're saying, oh, we're driving the qubit at 4.95 or 97. The first one says, I guess it's rounding this out. Maybe if I go to -1, you can see that the initial drive channel is sort of being specified here at 4.97. The 6.99 gigahertz, so this is the frequency of our readout resonator. So as I mentioned earlier, you want the readout resonator to be well detuned from your qubit so that you're in this dispersive limit. So the readout resonator ends up sitting up around 7 gigahertz in this case. But so nothing is too exciting here in the sense that you don't see changes in your pulse, but just for sake of demonstration, let's say I take my measurement pulse and set it to an amplitude of 1, then I guess it scales these two things here, but now this amplitude ends up being much larger than it was before. Just to avoid any funky behavior, we're going to go ahead and just keep that the same. So then now, this is where I'm actually going to go and run all these different schedules. So these schedules is where I'm sort of setting the assigned parameter, and I'm sweeping the different frequencies that are inside this part up here. And then now when I take the number, so I'm just going to, for sake of statistics and getting a decent signal to noise, I'm going to run at each frequency point 1,000 shots roughly. I'm going to run the schedules. Now, I talked about measurement level 1 or 2 or 0. For here, we're going to stick to measurement level 1. So this is where we're getting the IQ results. The measure return, I'm going to have it return the average of these 1,000 shots. So if I say instead wanted to train my discriminator, so I wanted to create my own sort of measurement level 2, then ideally to start, I would have this measure return the single instance of each one of these shots so that I could have a nice sort of scatter plot to actually create my discriminator. But I will go ahead and run this. And of course, I'm getting an error. What sort of error am I getting? This is an unfortunate error that happens sometimes, but if I just go ahead and resubmit it. So now it has ran that job. So I can I like to do this. If I do job.job.id, then now this here is the job ID. I can run this monitor here, and it's telling me that the job is queued. So I didn't get reservations or make reservations here, but I'm 4th position in the queue. So hopefully these other jobs won't take too long to run, but we'll go ahead and let this sit for just a couple of minutes. While letting this sit, let's go ahead and do this. So I need to wait for this to run. While waiting, I'm happy to take any questions that folks may have. And maybe what I can actually do in the time being is submit some other jobs.
I don't see any questions. So if anybody have a question, please unmute yourself and ask.
Just to avoid the queue issues. So generally the way this notebook is set up is that it finds the rough qubit frequency. Just because I'm waiting for the frequency sweep to run, I'm going to go ahead and do this so that we can run this. Let's go ahead, comment this out, and then do job.job_ID so that I can reset these things later. But so now I've submitted that. Here, while I'm doing this, I can do quantum. I often like to look at this perspective. You can see that my first job is still sitting in the queue. It should be going in about a minute. It says queue position 2. So we've gone 2 down the line. And then here we're in queue position 6 for the next one. So let's see. Yes. Okay. So I don't want to waste too much time sitting. Queue position 1, we're getting pretty close. In a few seconds. Depends on how long that job currently in the queue takes. Some of these may actually be jobs that you're all submitting. So if anyone in the group is submitting jobs, let me know how it goes, or we can talk and see what the results look like for everyone. So I'll come back here. Let's cut this out. So job equals backend retrieve job. Yes, I did see share the Python file. So yes, it is the Qiskit textbook. Let me go ahead and just share the exact link while I'm waiting. So I saw someone asked a question about the notebook that I'm walking through. So I just ended up submitting that there. Here, perhaps what I can do to make things go faster is switch my backend. So give me a moment while I set this up. I will find a backend I have access to that's a little less busy, hopefully. Let's try that. And I'll share my screen once I confirm this is working. Okay, nice. So at the very least, one job has gone through, and then I've also, let me just do this real quick. Okay. So let me go ahead and just share my screen. Okay, so this first job, I've just gone and looked. It finished executing just a moment ago, and we're still waiting in the queue for the Rabi oscillation. But so I retrieved my job, backend.retrieve job. Now I want to sort of see what the frequency sweep results are. If I run this, then lo and behold, here's the results that you see. So you start off sort of with, so the way that this is working, and perhaps I can bring up this notebook just to make it extra clear, this tutorial. So this is the two-tone spectroscopy, where what we're doing is we have one tone that's driving the qubit frequency. So that is dictated by the x-axis here. And then we have another tone that's sort of driving at the readout resonator frequency that we already know. So the goal that we're trying to achieve now is actually calibrating what this F01 is. So here we can see that as we sweep, we don't see much change until all of a sudden when we drive at some given frequency, we see a large shift in what the sort of measured signal from our readout resonator is. And then this ends up being the qubit frequency. So now we want to sort of fit to this. And when we do the fit, we can sort of do this. And then we can get a rough estimate that the qubit frequency is around 4.7172. You'll notice that the initial guess was safe, or the value that we had from the back end was this. I do want to emphasize this is just a rough qubit frequency calibration. I believe by the end here, it shows how you can do a fine frequency calibration. But this right here is just sort of giving you a rough value. So this would be the first step that you do. Now, there might be a question, hey, how do I determine what frequency my qubit is at? If I don't have this sort of pre-defined knowledge of what it is, in fact. And this comes from the design of the hardware, and that as you are designing the hardware, you will design it with a particular EC and EJ in mind, and it is the product of EJ and EC that will ultimately determine what your primary qubit frequency is, namely the F01 of your qubit. Perhaps we can look at this and see that it's still running. So from here now, we're actually going, so we've done the pi pulse, we've done the frequency calibration, and now we want to do these Rabi oscillations, which is sort of this component here. Before actually doing the Rabi oscillation, or while that's running, I just wanted to come over here. So I've taken up a different backend in which I have multiple qubit gates. So here we can say now I'm defining the instruction schedule map of that. So in this case, this is also just a single qubit gate. What's nice about this backend is it has two qubit gates. So I can say, look at qubits, the interaction between 0 and 1. So now here you can see that this is that same cross-resonant gate that we were driving earlier. Perhaps just to make this a bit interactive, if anyone's willing to speak up, which qubit in this case is behaving as the control qubit? Perhaps you can tell by the way I've drawn qubits here, or the schedule itself. Any ideas?
Zero.
Yes. Yeah. So it's the 0. So you might be inclined to think that the first one we write ends up being the control, but specifically you can also see that U0 is the channel on which your cross-resonant gate is on, and D1 is the one that has the rotary echo. So now we can make it a little bit more complicated. So as you get to higher numbers, all right. So let me pick 23 and 22. So now here is the difference for a different pair of qubits on this backend that I'm looking at. So I'm looking at pairs, the cross-resonant gate between, or the C0 gate between qubits 21 and 23. We can see, just because of the way numbering works when you start dealing with pairs of things, that the control channel is on U48, which makes it a little difficult to know. Which qubit in this case is the control? So I guess we could use the cheating thing and say, oh, it in fact is qubit 23, because I wrote it first and I knew that happened to be the case. But another thing that you can sort of look at is the target qubit is the one that has the rotary tone. So you can see here, 21 has this rotary tone. And so it's in this way that you know qubit 21 is the target. And then now if I just wanted to show, if I switch it, 23 instead, you can see that we're still keeping the control channel on U48, but we've added in these extra rotations before and after. And so this now is that Hadamard reversal gate. So I'll just allude to something, sort of the advanced section of the talk, which gets into this idea of the continuous gate set. Namely, what you're going to do is you're going to take these cross-resonant pulses. You can see that they're sort of called Gaussian square pulses. So what's nice is that they have these sort of Gaussian ends where they sort of ramp up like a Gaussian, but then it's a flat top in the middle section here. This flat top component ends up being really convenient to scale these pulses without extra calibrations, which is what I will discuss in the next section. First, I just wanted to get the R-Monk Rabi oscillation. Perhaps it will go faster if I run it on this backend. So Q position 1, it's already a bit faster, actively running, great. We're only doing 1,000 shots, and we haven't adjusted our rep rates or anything, so this is relatively quick. This is often the life of an experimentalist, is I sit here and run jobs and excitingly wait as it says that it is running. If I can work effectively, sometimes I'm able to multitask in these moments and set up other things as well.
এইটা না আমার ফোনটা
Okay, perhaps in the same way I can set this up to run the thing. Okay, so what I'm going to do is I'm going to let the experiments here run, and then successfully ran. So at least we got this. So then now we do this. And here you can see that the peak is actually very clean, and you end up getting something like this. Something that might be interesting to sort of study sometime yourself is you can see sort of power broadening. So if you take the drive amplitude here and you crank it up to the max value we allow is 1.0. But then if we were to run this at 1.0, you'd end up seeing that this peak will be much broader. And this is sort of known as power broadening, and it's one way that you can actually cause your qubits to have poor coherence. But for the sake of our demo, let's just march on forward. My fit has gotten messed up for some reason, which is a funny thing. So it's because it's guessing the wrong value, I think, here. So I think I know my qubit frequency, say 5.09. Maybe that will fix it. Okay, so I'm not going to do live debugging on my fits, but I will wait for the result from harmonic. Yay, it finished. Okay. Getting back to where we were. So we ran this fit. We saw that we had our qubit frequency here. And so now we've sort of had the rough estimate, and now we're going to do these Rabi oscillations. So we set to do the Rabi oscillations. What we're going to do, we're going to say have 50 different points that we're going to start. We're going to start with an amplitude of 0. I'll show you what this looks like, and then go to a max amplitude of 0.75. These are in arbitrary units. It gets translated to some sense of power that goes inside the fridge. In principle, you could actually calibrate how many photons you have inside the fridge with some different experiments. But then the drive amps here, now you're setting it up to go from the min to the max as you just set with the number of points. Earlier, we set our rough qubit frequency to be the backend default. So I will just do that again. So these Rabi oscillations were done with that instead of with this rough calibration that we did. And that was just in the sake of time. No particularly important reason. So now this here is a bit different than what we had before. A lot of it is the same, except now instead of sweeping over the frequency like we did in the past. So the last time we set the frequency when we were setting different frequencies, here we're going to set the frequency sort of to be one thing. And instead now we're going to sweep the drive amplitude from this list right here. So when we do that, so then we can look at something like this. So the very first drive amplitude has some pulse, or sorry, so this say actually is the last Rabi pulse that we have. And you can see that it has some amplitude. If I go to the very, very first one, you can see that that pulse goes away. And that's because we start off with a 0 amplitude. And then if I look at the first one, it's there. And what you can't necessarily see is that it's sort of being rescaled in this axis. So then now I could run this again, but I don't need to. So instead I will do job equals backend dot retrieve job here. Do this. So these are our Rabi results. And we have our Rabi results. So we are doing, so it's in sort of arbitrary units here on the y-axis. You could change this to say population in your 0 state or population in your 1 state using sort of that measurement level 2 approach where you actually create the discriminator. But in any case, you can see that you have these nice oscillations going from where you start off in your ground state when there's 0, amplitude, and then you go to the excited state, back down to the ground, excited, so on and so forth. And then now, once we actually wanted to do this, we do some fit where you can then end up seeing that going from sort of, say, the excited state point here to the ground state, we have some amplitude of pi. And so now this is our pi pulse, and this is at the way that you end up dictating what your Rabi oscillation is. So now if I wanted to do that calibration that I talked about before, I'd say pi over 2 amp equals pi amp divided by 2, and then say print this. So now this would be my pi over 2 amplitude. And then now I can say, create a schedule in which I sort of repeat this many times. When I repeat it many times, I'd end up doing something that looks a bit like this here, where it does the ping pong type fashion. And then now I can sort of finely adjust what this amplitude is here in order to get a fine amplitude calibration. And this is some of the basics on how you would do your Robbie oscillations and how you calibrate some of your gates. Please do go through the notebook. There's a lot more going on here in the sense that we have how you actually can construct that measurement level 2 feature. And then in subsequent, and so here's your 0, 1, you can then adjust the duration of your readout pulse if you wanted to see these two blobs come together or go further apart. You can do this as a way to measure the T1 of your qubit. So I didn't touch on this too much, but T1s and T2s are the very important values for our devices. IBM with a transmon recently showed a T1 of on the order of 1 millisecond, which is quite exciting. And then you can also do this as a way to say measure. So this here is doing the Ramsey oscillations. You can then sort of fit, and then from this, you're seeing that you're sort of detuned from the actual qubit frequency by some amount. So then you can sort of adjust that. And then also do Hahn echoes to measure your T2 and see how you can improve it through dynamical decoupling with a CPMG chain. So this is the demo and the basics of it. I have other things that I can show if there's questions. Otherwise, I'll just get to the advanced section and talk about this continuous gate set. Let me see. I see that Talat wrote 21 in the chat. I don't know if there was a question or if that was somehow specific.
I think the 21 was from your question that which gate is the control gate. Anyway, so...
nice, yes.
So there is no question in the chat. So I have one thing. So this pulse feature, can we somehow use it as a dynamical decoupling thing now, or it's not feasible right now?
Yeah, it is absolutely feasible. So you can use the pulse feature to do dynamical decoupling. In principle, actually, you can do dynamical decoupling even at the circuit-based level through adding in gates with barriers and what have you. But you can absolutely do it with pulse as well. And I think what's really interesting about pulse is that you can, so I talked about this Gaussian shaped pulse. That's just one way in which you can create a pulse. There is research that people do where they, into the pulse itself, build in this essence of dynamical decoupling so that the pulse achieves the gate that you want while also achieving some sort of echo type feature inside of it. So there's a startup based in Australia, Q Control, where they do some work like this. And I can point to a Qiskit blog that writes about that. But to your question, yes, you can absolutely use this pulse stuff to construct dynamical decoupling schemes, do it with very fine resolution in your time, say, or construct exotic gates.
Okay, thank you. So I think if there is any other question, please speak up. Otherwise, we can move on to the next part of the talk, maybe.
Give it a few seconds just in case. Right, great. In this case, let me go ahead and bring up this. Right. Share my screen. Okay. Does everyone see my PowerPoint slides again?
Yeah.
Great. So earlier I left on this note of if you do optimization level 3, for this CRX gate or CRZ gate, then for any angle other than pi, the most optimal that you can do is sort of this 2C0 version. What this doesn't pay attention to is the fact that your cross-resonant gate actually is a ZX of theta interaction. So in earlier slides, let me go back, I talk about how the cross-resonant gate ends up giving you this sort of ZX of theta, where in the specific case, I can, if I wanted to build a C0, it's convenient to use a theta of pi over 2. And then through constructing that with that pi over 2 and a ZI and an IX in the negative pi over 2, I get my C0. But in the more general case, I still have this theta. And this is where you can actually leverage this sort of arbitrary angle that exists within the ZX of the ZX interaction as a way to have a more efficient implementation for some gates. So specifically, this CRZ here, or CRX, say in some cases, or CRY, I'll talk about all of them in a moment, is something that naturally starts to happen as you're tuning up your gate. So as you take your your cross-resonant tone, and you do Rabi-like oscillations or Rabi-like experiments where you start to see oscillations on your qubit, what you're inherently doing is you're getting these partial rotations of the qubit. So in some sense, if you think about your gate calibrations in this way, you can realize that you actually are getting natively through the cross-resonant interaction, these interactions instead of needing to use the 2C0. So the 2C0 version is not necessarily the most efficient way in which you could do it. And this gets to this idea of continuous gate sets. So for continuous gate sets, I'm going to take this sort of C0-like schedule that I had shown you before, and I'm going to take that ultimately how much it rotates, assuming everything behaves linearly, will just depend on the area under the curve. So the area under the curve for this flat top Gaussian is sort of given by this, where A star is, say, or alpha star is representing the initial calibration values. So then this has some characteristic amplitude, A star, some characteristic width D star, and some characteristic total duration D star. And then the area sort of adds up as you see here. So now if I wanted to do a partial rotation, what I can then do is assume that I can scale the area under this curve in a sort of linear fashion. So I'll start off. Particularly for the cross-resonant gate, the amplitude aspect is a nonlinear. It tends to be very nonlinear, particularly when you've tuned it up to be the fastest that it can be. So instead of adjusting the amplitude at the start, what I'd like to do is adjust the width of this flat top Gaussian component. So this is where I'm going to say that the width is some parameter or somehow now dependent on the theta that you wish to rotate. And basically I do that by adjusting this the area under the curve. So here I'm going to say that if I want to rotate by some amount theta, I'll normalize that by the amount of pi over 2 in the alpha in the area there. And then this now will dictate the new area that I actually wish to have. And then in order to achieve that area, I just begin to adjust the width of this pulse. Then by doing so, I can actually now get some partial rotation without doing any extra calibration. So in principle, if you wanted, you could go and do these gate calibrations yourself and then see the continuous gate set as you're doing the calibrations. But calibrations are sometimes a bit tedious and difficult to do. So the goal here is to show how you can take this and achieve this with no extra calibrations. Once the width is 0, so once you no longer have any flat top Gaussian, you have two options at this point. You can either begin to sort of tune the rise and fall of these pulses here, or you can begin to tune the amplitude at this point and adjust the amplitude in order to get the desired area under the curve. For the sake of the sort of work here and some of the follow-up work that we've done, we decide to keep the rise and fall time sort of fixed simply because this is something that As I mentioned at the start, if you make your pulses too fast, you start to get excitations, and this isn't the ideal thing that we want to have. So to reduce that sort of error, we instead just sort of adjust the amplitude. And when you do this, this now is sort of benchmarking, say, for that CRX or CRZ type gate, how you can perform relatively. So the blue triangles here, this is doing quantum process tomography, which is a way to characterize what sort of unitary you're actually implementing on your backends. And specifically, you can use this as a way to get an essence of a fidelity. So the blue dots here are the sort of default version if you use this gate-based transpilation and you have a double C naught, whereas the orange is sort of this parametric version where you're going to do this scaling. And you can see that as your angle gets smaller, so the desired rotation that you wish to have, as that gets smaller, what's happening is the width or duration of this pulse also ends up becoming smaller. And then by reducing the duration of this, you actually end up getting an improvement in the overall fidelity of the gate that you're trying to implement. So now this is showing, say, in the context of a CRX type gate and how you can achieve a relative improvement when compared to the double C naught. This isn't the only thing that you can do. You can actually do it for some other things. So here I just mentioned this sort of CRX type gate. You can also say do it for CRZ or a CRY. The CRZ, say, is useful particularly in QAOA, also useful for Pali feature maps and quantum machine learning. And then the CRY, say, is useful for some sort of portfolio optimization type things. So now, how is it that this works? Well, before I talked about this cross-resonant interaction and how you can build a CX from that, one thing I didn't mention at the time is that the cross-resonant phase is something that you can tune as well. And by adjusting the phase of your cross-resonant tone, you can adjust yourself from being a CX type gate to being a CY type gate. So now we've achieved an ability to get the CX as well as the CY. And then furthermore, what's nice is that the CZ gate is sort of locally equivalent to our cross-resonant gate. Namely, so we have that ZX type interaction. So if on your target qubit you apply Hadamard's before and after, this ends up end up giving you a ZZ type interaction. So you take this ZX and you're applying Hadamard's on the X, which turns it into a Z. And then now you can have your CZ of theta type interaction here. And so now we can get CY, CX, and CZ. What is an exciting thing that you can do once you generalize to these different rotations is you can now bring in what's sort of known as CAC decomposition. So this is where I want to implement an arbitrary SU4 gate. There are different ways that you can implement arbitrary SU4 gates. You can do it with a basis gate set that is built with C naughts. So that's sort of what's shown here at the bottom. When you do that, you have 3 C naughts with corresponding RZ gates or the U1 or U2 type gates here. So there's some definitions that I can get into if interested with what these U1s actually are. Alternatively, you can also, instead of transpiling to a C0 basis gate set, you can transpile to a basis gate set that leverages these sort of continuous gates. So the RXX, RYY, or RZZ. And then you have single qubit gates before and after. When you do that, in the same way that taking that CRX gate and scaling its duration allowed us to get an improvement for sort of that specific component, you can, here we sort of demonstrate that you get an improvement for arbitrary SU4s. So, and this really does come down to the relative duration of the schedule. So if you pick some parameters that specify specific location in your SU4 space, then here you can show that this sort of continuous based gate set approach gives you a relative improvement. And then just to bring it back to some QAOA type features, if you have this this sort of C0, RZ C0, so this alone was the thing that we had improved before. But if you include a swap gate afterwards, which has those 3 C0s, then you can actually sort of decompose this efficiently using this CAC decomposition as well and translate this into a sort of continuous basis gate set as well. That is my presentation. And I think I will stop here and take any questions that I have. Otherwise, I think I am done.
So I still don't see any question in the chat box, but if anybody have any question, please unmute yourself and ask. I think your presentation was so good that nobody have any question. Anyway, so can you just tell me if where do I find what does every optimization schemes do, like 0 to 3? What exactly are being done there?
That's a very good question. You're talking about the optimization level for the transpiler. It's a good question. There is some documentation somewhere. I can't recall off the top of my head exactly where it's located. I need to spend a little time looking into that. What I can say is that it just goes to sort of more sophisticated optimization. So 0, for example, only takes into account the connectivity and does nothing else. Level 1 sort of looks locally and sees where you have gates that you can collapse together. So for example, if you have a series of single qubit gates, all one after each other, in principle, and then there's nothing else going on around them, you can collapse those all down into sort of one single gate or maybe 2 single qubit gates. So that would be like level 1. Once you get to level 3, it actually starts to look at the unitaries that are being implemented on the circuit and find sort of equivalences that sort of help improve things. Each one of these is its own essence of a transpiler pass. How you define the transpiler pass is, I think, that we're trying to create a standard in which it's done. But what a transpiler pass is, you can optimize in whatever way you sort of want. So there's a lot of different ways that you can choose to optimize. For example, this pulse efficient idea that I just brought is a different way of optimizing a circuit and can be included as a transpiler pass. So it can be part of those optimization levels. To get to your exact question of what each one of those levels is doing, I need to look into the documentation to find out.
Okay, thank you very much, and thank you for the wonderful talk. It has been very educational. So if there is no questions, I think we can call it a day. And
yeah, I just want to add that I was also around. In fact, it's very well explained. And most of the students are getting exposed to it for the first time. So that's the reason probably you did not get much questions, but I'm sure they would get used to it. And truly appreciate your presentation. Extremely good presentation.
Thank you so much. I'm excited that everyone's able to start learning this. Please always feel free to ping me or ping folks on the Qiskit channel. It's an exciting thing to get into this. Thank you all.
Thank you.
Great. I'm seeing all the thank yous. Thank you all so much.
Okay. So can we just end the presentation for everyone?
Yes,
Thank you
you are
so
saying
much,
something.
everyone.
Yeah. Shreya, you are mentioning something.